Chemistry is a highly high-yielding and mathematical section. The exam heavily tests rigorous derivations, precise application of the IUPAC sign convention, and numerical accuracy. The selected question and answer pairs below reflect the exact technical depth and structural format required to score highly in the mains examination. Question 1, 15 marks. A. State the physical significance of mean ionic activity coefficient, gamma_PM. B. Derive the Debye-Huckel limiting law from underlying assumptions. Model answer. Part A. Physical significance of mean ionic activity coefficient, gamma_PM. In an ideal solution, solute particles do not interact with each other. However, in real electrolyte solutions, strong long-range electrostatic forces exist between ions even at low concentrations. The activity A represents the effective concentration of an ion in a real solution. The mean ionic activity coefficient, gamma_PM, measures the deviation from ideal behavior resulting from these enterionic attractions. Physically, gamma_PM less than 1 indicates that enterionic attractions stabilize the ions in solution, reducing their chemical potential compared to an ideal state at the same concentration. Part B. Derivation of the Debye-Huckel limiting law. 1. Underlying assumptions. Complete dissociation. The strong electrolyte is completely dissociated into ions in the ions are treated as spherically symmetric point charges. Their finite volume is neglected. Dielectric continuum. The solvent is treated as a continuous medium with a uniform macroscopic dielectric constant, epsilon. Thermal versus electrostatic balance. The distribution of ions is governed solely by a balance between thermal motion, Boltzmann distribution, and electrostatic forces, Poisson's equation. 2. Mathematical derivation steps. Step 1. Poisson's equation. The electrostatic potential, psi at a distance r. Step 3. Debye-Huckel linearization approximation. For dilute solutions, the electrostatic energy is much smaller than the thermal energy, Z_IE, psi, K_BT. Expanding the exponential via Taylor series, xp, x, approx 1x. Step 4. Combining Poisson and Boltzmann equations. Substituting ρ back into Poisson's equation, where kappa is the Debye screening parameter, defined as the reciprocal one. Kappa is known as the Debye length, the thickness of the ionic atmosphere, which boundary condition, psi, to 0 as r, to infinity, is. For a highly dilute solution, kappa r, L1, expanding the exponential gives. The second term represents the electrical potential, psi_text, ATM, contributed exclusively by the surrounding ionic atmosphere. Step 6. Relating potential to activity coefficient. The electrical work done to stabilize the ion by its atmosphere matches the excess chemical potential, delta, mu_I equals K_BT, ln, gamma_I. The charging work is converting to the mean ionic activity coefficient, gamma_PM, and expressing concentration in terms of ionic strength, I equals, frac 1, 2, sum m_I_z_I squared, we arrive at the Debye-Huckel limiting law, where A is a constant depending purely on temperature and properties of the solvent. A, approx 0.509, text, mole, 1/2, text, kilogram, 1/2, for water at 298 K. Question 2, 10 marks. Set up a concentration cell without transference containing 2 hydrogen electrodes immersed in solutions of different hydrogen ion concentrations. Derive the expression for its EMF at 298 K. Model answer. 1. Cell schematic representation. A concentration cell without transference consists of 2 distinct half cells connected via a salt bridge to eliminate liquid junction potential, LJP. 2. Electrode reactions. At anode, left electrode, oxidation. At cathode, right electrode, reduction. Net cell reaction. 3. Derivation of EMF using Nernst equation. The standard EMF of any concentration cell, E_circ_text cell, is identically 0 because both electrodes are made of identical chemical materials. Applying the Nernst equation at 298 K, N equals 1. If we assume the solution behaves ideally, activity A can be approximated text cell greater than 0, log_10, A_2, A_1 must be greater than 0, confirming our initial physical constraint that A_2 greater than A_1. Question 3, 10 marks. Numerical practice. Calculate the mean ionic activity of a 0.01 text mole kilogram, -1 aqueous solution of text L_2 text SO_4 _3 at 25 degrees Celsius. Given A equals 0.509 for water at 25 degrees Celsius. Model answer. Step 1. determine the ionic strength, I, of the solution. Text Al_2, text SO_4, _3 dissociates completely as follows. Given molality M equals 0.01, text mole kilogram, -1, molality of text Al, 3 plus, M_ plus, equals 2, times 0.01 equals 0.02, text mole kilogram, -1, with charge Z_ plus equals +3. Molality of text So, 4 2, M, equals 3, times 0.01 equals 0.03, text mole kilogram, -1, with charge Z_ equals -2. Calculate ionic strength, I. Step 2. Calculate log_10, gamma_pm, using the Debye-Huckel limiting law. Step 3. Calculate mean ionic molality, M_pm. Step 4. Calculate mean ionic activity, A_pm. Key structural framework for topping chemistry optional. Always label signs cleanly. Clearly highlight standard states and specify whether you are defining standard reduction potentials or standard oxidation potentials. Dimensional units. Never omit your units, text mole kilogram, -1, text V, or text J mo, -1, during numerical substitutions or final answers. This is where examiners cut critical partial marks.